It's a night unlike any other, a vast, unbroken expanse of darkness, interrupted only by the cold, distant glow of ancient stars. The blackness of space stretches in all directions, infinite and unyielding. Here, in this silent abyss, time itself seems to lose its meaning. You are an astronaut, floating freely, untethered from your spacecraft. The Earth, a brilliant, swirling marble of blue and white, spins silently below you, a familiar and comforting sight in the overwhelming emptiness. Yet something feels off, a subtle, almost imperceptible wrongness. You glance at your wristwatch, a habit from a world of schedules and deadlines, expecting to see the familiar, steady tick of seconds marching forward. But the hands seem sluggish, reluctant to move, as if they are pushing through an invisible, viscous medium. You blink, shake your head, and look again. Nothing has changed. The hands are still crawling at a snail's pace. Then, a flicker of movement catches your eye in the periphery. The distant stars, which should be constant, unwavering points of light, appear to twinkle at irregular, unsettling intervals. Their light seems stretched, distorted, as if reality itself is bending and warping around you. On board the spacecraft, just a few meters away, your crewmates continue their routine, their voices a faint, tinny murmur in your earpiece. You can see them through the viewport, checking instruments, conversing, floating effortlessly in the familiar embrace of microgravity. Their movements appear normal, their time flowing at the expected, predictable rate. But out here, where you drift alone in the void, time is different. You take a deep, ragged breath, the sound of it loud and alien in the silence of your helmet, trying to calm the rising sense of unease. You have studied this phenomenon before, in textbooks and simulations. Time dilation, a strange and wonderful prediction of Einstein's theories of relativity. But now, experiencing it firsthand, you feel something deeper, something more unsettling than any equation could ever convey. A question, ancient and profound. Echoes in the silent chambers of your mind, what is time? From the moment we are born, we live under the inexorable rule of time. It is the invisible, and often tyrannical, metronome that dictates the rhythm of our lives. It marks the passage of our existence, from the fleeting innocence of childhood, through the striving and struggles of adulthood, to the quiet reflections of old age. It determines when we wake, when we work, when we eat, when we rest. We measure it with our clocks. We count it in our calendars. And we often fear its relentless, unidirectional march forward. But what if this most fundamental aspect of our reality, this thing that seems to govern our every moment, is not as real as it seems? What if everything we experience, the past, the present, the future, is not a flowing sequence of events, but exists simultaneously, a vast, frozen landscape of now? What if time does not flow at all? To us, time feels like a river, a current that carries us inexorably from the fixed, immutable shores of the past towards the unknown, open waters of the future. But some of the greatest and most courageous minds in human history have dared to question whether this powerful, intuitive perception is a true reflection of reality, or is merely an elaborate and deeply convincing illusion created by the workings of our own consciousness. If we could somehow step outside of the universe, if we could adopt a God's eye view and look at time from a higher, inaccessible dimension, what would we see? Would we see a linear, unfolding story, a film playing out from beginning to end, or would we see the entire film at once, every single frame, the first and the last existing simultaneously in a single, timeless, four-dimensional block? The implications of this are profound and deeply unsettling. If time is an illusion, If the future is as real and as fixed as the past, then our cherished and deeply held belief in our own free will may also be an illusion. Every decision we make, every action we take, every single creative thought we have might already be determined, already written into the unchanging script of the cosmos, like a film reel where the ending is already printed on the celluloid. But we, as characters in the story, can only watch it unfold, moment by agonizing, beautiful, and seemingly spontaneous moment. The nature of time has been a battleground for philosophers and scientists for millennia. The ancient Greek philosopher Parmenides, in the 5th century BC, argued that change itself was an illusion. For him, all of reality was a single, static, and unchanging whole, a perfect and eternal sphere of being. Our perception of a flowing, changing world was merely a trick of our unreliable senses, a fleeting and deceptive shadow play on the walls of our mental cave. To Parmenides, the past, the present, and the future already existed, fixed and immutable, and what we experience as the now was just our limited, and ultimately illusory, perspective on this eternal, timeless reality. His ideas stood in stark and dramatic contrast to those of his contemporary, Heraclitus, who believed that change, or flux, was the fundamental and only nature of existence. "No man ever steps in the same river twice," he famously said, "for it's not the same river, and he's not the same man." For Heraclitus, time was not an illusion to be seen through. It was the very essence of reality, the creative and often destructive fire that was constantly shaping and reshaping the universe in an endless, dynamic process of becoming. These two, diametrically opposed ideas, time as illusion versus time as reality, set the stage for thousands of years of intellectual and philosophical debate. Plato, in the shadow of Parmenides, saw time as a moving image of eternity, a mere imperfect reflection of a deeper, timeless, and more real realm of perfect, unchanging forms. His student, Aristotle, took a more practical and in many ways more modern view. He disagreed with the idea of time as an independent, existing entity, arguing instead that it was simply a measure of change. For Aristotle, time was real, but only in relation to the motion and the unfolding of events in the physical world. It had no existence of its own, beyond its role as a way of quantifying the universe's dynamic processes. For centuries, the debate continued, but the dominant view, the one that would come to shape the scientific revolution, was that of time as an absolute, independent entity. When Isaac Newton formulated his revolutionary laws of motion and gravity in the 17th century, he imagined time as a universal, cosmic clock, ticking away at a constant, unvarying rate for all observers, everywhere in the universe, completely independent of the space and the matter that it contained. For Newton, time was like an invisible and infinitely long thread stretching across all of existence, providing a fixed and absolute backdrop against which all the events of the cosmos could be unambiguously ordered and measured. But then, in the early years of the 20th century, everything changed. A young, and at the time unknown, patent clerk in Bern, Switzerland, named Albert Einstein, completely shattered Newton's elegant, but ultimately incorrect, vision of time, with his special, and later his general, theory of relativity. Einstein showed that time was not an absolute, independent, and universal force. It was fluid, it was flexible, it was elastic, and most profoundly, it was deeply and inextricably connected to space itself. Space and time. Einstein argued, were not separate entities, but were two aspects of the same, underlying reality, a single, four-dimensional fabric that he called spacetime. The consequences of this idea were staggering, and they have been confirmed by a century of precise and rigorous experimentation. Relativity tells us that time can be stretched and contracted, that its passage is relative to the motion and the gravitational environment of the observer. The faster you move through space, the slower time passes for you relative to a stationary observer. The stronger the gravitational field you are in, the more time slows down. Bending under the immense weight of the universe's most massive objects, time was no longer a universal, cosmic constant. It was a local, personal, and dynamic phenomenon, changing its rhythm and its flow, depending on where you were and how you were moving. This was not just a theoretical speculation. Atomic clocks, the most precise timekeeping devices ever created by human hands, when placed on fast-moving jets or on high-altitude GPS satellites, have been shown to tick at slightly but measurably different speeds compared to their identical counterparts left behind on the surface of the Earth. The implications were profound. If time could be stretched and warped, if its passage was not the same for everyone, then what did that mean for our everyday, common-sense experience of reality? Could time, as we understand it, as we feel it, even be real? Perhaps the most radical and most mind-bending implication of Einstein's unified space-time was the idea of the block universe. If space and time are truly woven together into a single, four-dimensional fabric, then this fabric must contain all of time, just as it contains all of space. The universe is not a film reel that is playing out from beginning to end. It is a completed film, a single, static block of space-time, with every single frame, every moment in history, from the first flicker of the Big Bang to the final, dying embers of the last stars already in place. In this view, the past is not gone, and the future is not something that has yet to arrive. All moments, past, present, and future, exist equally, simultaneously, like different and equally real locations on a vast, four-dimensional map. What we perceive as the flow of time, the feeling of the now moving forward, is merely the path of our own consciousness, the subjective journey of our awareness as it moves along its fixed, predetermined world line through this unchanging, four-dimensional structure. If the block universe model is a correct description of reality, then the future already exists, just as surely and as concretely as the past does. The moment of your birth, the moment you are experiencing right now as you listen to these words, and the moment of your death are all equally real, all frozen into the eternal, crystalline structure of space-time. This is an idea that is deeply and profoundly difficult for the human mind to grasp because it contradicts our most basic and powerful intuitions. We feel time moving forward. We feel it slipping through our fingers like sand. We experience the past as a fixed and unchangeable memory, and the future as an open and unwritten book. But all of this, in the block universe view, may be nothing more than a powerful and deeply convincing illusion, a trick of our perception, a story that our consciousness tells itself to make sense of a reality that is far stranger and more static than our senses can comprehend. And if this is true, it raises a host of deep and deeply unsettling questions about the nature of our own free will. If the future is already written, if every event is already laid out in the four-dimensional map of space-time, then are we truly making choices? Or are we simply actors in a grand cosmic play, following a predetermined script, believing ourselves to be in control, when in reality, every action we take, every thought we have, every choice we seem to make is already fixed, already embedded in the unchanging structure of space-time? Some scientists and philosophers argue that this is the only logical conclusion. If time is truly just another dimension, like space, then the idea of changing the future is as nonsensical as trying to change a particular coordinate in space. The future does not unfold, it simply is, but not everyone agrees with this stark and somewhat bleak interpretation. Some physicists argue that the block universe picture, which is rooted in the classical deterministic world of general relativity, is not the whole story. They argue that time is not a fundamental aspect of reality, but is an emergent property, something that arises from the deeper, more fundamental, and more mysterious laws of quantum physics in the strange and counterintuitive world of quantum mechanics. Time behaves in bizarre and unpredictable ways. Particles can exist in a superposition of multiple states at once, their futures seemingly undecided until the very moment they are measured. Some interpretations of quantum mechanics suggest that reality itself does not have a single, fixed timeline, but instead branches into a vast and constantly growing tree of possibilities. This has led to the concept of the growing block universe, a kind of middle ground between the eternalism of the block universe and the presentism of our everyday experience. In this view, the past and the present are real. They exist. But the future does not. Not yet. The universe is constantly growing, constantly expanding, with new moments, new slices of time, being added as reality unfolds. The future is not predetermined. It is being actively and dynamically created, moment by moment. Its path shaped by the inherent, irreducible uncertainty of the quantum world, and perhaps by the choices of conscious living beings. This concept of a growing, open-ended universe aligns much more closely with our own subjective experience of time. We feel the past as something that is fixed, something that we can remember but cannot change. The future, however, feels uncertain, open, a realm of possibility that we can anticipate, but do not yet see. The growing block universe model suggests that this feeling is not an illusion, but is a true reflection of the nature of reality. The present moment becomes a special and physically real frontier, the very edge of existence, the place where the quantum probabilities of the future are collapsing into the classical certainties of the past. It is the place where reality is being forged. And yet, even this more intuitive idea raises more questions than it answers. If time is truly something that is being created, then what is the mechanism of this creation? What determines how, and at what rate, it unfolds? If the future is not fixed, then what guides the path it takes? And if quantum mechanics allows for a multitude of different possible futures, does that mean that there are multiple parallel realities, alternate timelines that are constantly branching out from our own with every quantum event, with every choice we make? Some scientists and philosophers believe that the ultimate answer to these profound questions may lie not in the external world of physics, but in the internal world of consciousness itself. Our perception of time is so deeply and intimately tied to the way our minds process information, to the very structure of our own conscious awareness. We experience life as a linear sequence of moments, one following another, and this creates the powerful and compelling illusion of a flowing, moving present. But this experience may not be a true reflection of the fundamental nature of time. It may be a feature of our consciousness, a useful and adaptive mental model, rather than a fundamental property of the universe. In this view, our consciousness does not move through time. It simply exists, sequentially, at different points along a pre-existing timeline. In the same way that we only experience one specific location at a time as we move through space, we only experience one single moment at a time as we seem to move through space-time. But all of those other moments, the past, the present, and the future, are equally real, all just waiting in their own specific coordinate in the block universe, to be observed, to be experienced. to be illuminated by the moving flashlight of our own. Conscious awareness. This is an idea that is incredibly difficult for the human mind to grasp because it contradicts everything we feel, everything we intuitively know about the nature of time. But if the great scientific revolutions of relativity and quantum mechanics have taught us anything, it is that the universe is far stranger, far more mysterious, and far more beautiful than we could have ever imagined. The familiar, comforting, and seemingly relentless flow of time may be nothing more than an elaborate trick of our own perception, a mental construct that our brains have evolved to make sense of a reality that is far more complex, more static, and more wonderfully timeless than our senses can ever directly comprehend. As you continue to float in the deep, silent void of space, as you watch the Earth slowly, majestically, turn below you, you begin to wonder, is this moment happening now, or has it already happened, 1,000,000 years ago? In the mind of a distant, alien observer, could the future already be written, a story waiting for you to reach its final page? Or is it still being created, its narrative shaped by choices you have yet to make? Perhaps time is not something we move through. Perhaps it is not something that exists at all, in the way we think it does. Perhaps time is simply the way we, as conscious living beings, experience a universe that is already and forever complete, a vast, silent, and eternal tapestry, with every moment laid out, like the infinite, shining threads of a cosmic poem, waiting, unchanging, and beautiful. The idea that our universe is a vast, four-dimensional block of space-time, a static and unchanging reality where all of time exists simultaneously, is a profound and deeply unsettling one. But if it is correct, it raises a tantalizing and inevitable question: if time is just another dimension, like space, can we move freely through it? Can we, in principle, build a machine that could carry us back to the past, to witness the rise of ancient empires, or to meet our own ancestors? Or could we leap forward into the distant future, to see the fate of our species and the ultimate destiny of our world? Science, in its rigorous and often counterintuitive way, suggests that one of these journeys is not just possible, but is a proven and observable fact of our reality. In 1971, in a simple but brilliant experiment, the physicists Joseph Haffel and Richard Keating took a set of highly precise cesium beam atomic clocks and placed them on commercial airliners, flying them around the world, first eastward and then westward. When they returned and compared these airborne clocks to identical, synchronized clocks that had remained stationary on the ground at the U.S. Naval Observatory, they found something astonishing. The clocks that had traveled on the moving planes had ticked at a slightly, but measurably, different rate than the clocks that had stayed behind. Time itself had passed differently for the travelers. This was a direct and stunning confirmation of the time dilation predicted by Einstein's theories of relativity. The faster you move through space, the slower time flows for you, relative to a stationary observer. This means that if a person were to embark on a journey in a spaceship traveling at a significant fraction of the speed of light, they could experience time at a dramatically slower rate than the people they left behind on Earth. A crew of astronauts could travel to a nearby star system and back, a journey that might feel like just a few years to them, only to return to an Earth where centuries or even millennia have passed. In a very real and physical sense, they would have traveled into the future. This is not just a theoretical possibility, it is a constant and necessary consideration in our modern technological world. The high-energy particles called muons, which are created when cosmic rays from space slam into the Earth's upper atmosphere, are a beautiful everyday example of this. These muons have an incredibly short lifespan, They should decay in just a few millionths of a second and should never have enough time to survive the long journey from the upper atmosphere to the ground. And yet, we detect them here, on the surface of the Earth, in large numbers. The reason is that because they are traveling at very nearly the speed of light. Time, from their perspective, slows down dramatically. Their internal biological clocks tick much more slowly than ours, and they live long enough, from our point of view, to complete their journey. Every single astronaut who has ever lived and worked on the International Space Station is, in a small but real way, a time traveler. Their bodies aging just a tiny fraction of a second slower than the rest of us on Earth. Time travel to the future is not just possible. It is a constant and well-verified feature of our relativistic universe. But while the journey forward in time is allowed by the known laws of physics, the journey backward is a far more problematic and far more philosophically fraught proposition. If time travel to the past were possible, it would seem to open up a Pandora's box of logical paradoxes, contradictions that threaten to unravel the very fabric of causality. The most famous of these is the grandfather paradox. Imagine you build a time machine, travel back to the year your grandfather was a young, unmarried man, and for some strange and malevolent reason, you prevent him from ever meeting your grandmother. As a result, your parent is never born, and therefore you are never born. But if you were never born, how could you have possibly traveled back in time to commit the act in the first place? The very success of your mission seems to erase the possibility of you ever having embarked on it. It is a perfect and seemingly inescapable logical loop. And the paradoxes do not stop there. There is the bootstrap paradox, or causal loop, where an object or a piece of information seems to have no origin. Imagine you are a struggling playwright. A mysterious time traveler appears and gives you a copy of the complete works of William Shakespeare. You then spend your life publishing these plays under your own name, becoming the most famous playwright in history. Then, in your old age, you build a time machine, travel back in time, and give the same volume of plays to your younger, struggling self. The question is, who wrote the plays? They seem to exist in an eternal, self-creating loop, without ever having been written. These paradoxes suggest that there is something deeply, and perhaps fundamentally, wrong with the idea of backward time travel. Physicists and philosophers have proposed several ingenious ways that the universe might conspire to avoid these contradictions. One idea is the Novikov self-consistency principle, proposed by the Russian physicist Igor Dmitrievich Novikov in the 1980s. This principle states that the laws of physics are such that any event that would lead to a paradox simply cannot happen. The probability of such an event occurring is zero. If you were to travel back in time and try to change history, the universe would subtly and inexorably prevent you from doing so. Your gun would jam, your car would break down, you would have a sudden, inexplicable change of heart. Your actions would be constrained in such a way that they always and inevitably lead to the very history that you were a part of. In this view, you can travel to the past, but you cannot change it. You can become a part of the past, but you cannot alter its course. Your presence was, in a sense, already factored in. Another, and perhaps even more radical, possibility is that the universe avoids paradoxes by splitting into multiple parallel timelines. This is the many worlds interpretation of quantum mechanics, applied to the problem of time travel. In this view, every quantum event, every choice, every possibility, causes the universe to branch into a new, parallel reality. If this is the case, then traveling to the past would not take you back into the history of your own original timeline. It would take you to a new and slightly different branch of the multiverse. In this alternate reality, you would be free to act as you please. You could, in principle, prevent your grandparents from meeting, but this would have no effect on your own original timeline. You would simply have created a new parallel universe where you were never born, while your own original universe continues on, unchanged. This is an idea that is often explored in science fiction, the idea of creating alternate histories. It neatly resolves the paradoxes, but it does so at a high price. It means that true time travel, in the sense of returning to your own personal past and changing it, might still be impossible. And it means that any time traveler would be forever marooned in an alternate reality, an orphan of time, forever cut off from the world they came from. But even if the universe has a way of dealing with the paradoxes, there is still the immense and perhaps insurmountable practical challenge of actually building a time machine. The laws of physics, as we currently understand them, do allow for the theoretical possibility of closed time-like curves, which are paths through spacetime that loop back on themselves, allowing an object to return to its own past. In 1949, the great logician and mathematician Kurt Gödel, a close friend of Einstein's, discovered a strange and disturbing solution to Einstein's equations of general relativity. He found that in a universe that was rotating, it would be possible for an object to follow a specific trajectory and to arrive back at a point in its own past. But our own universe, as far as we can tell from our observations, does not appear to be rotating in the way that Gödel's model requires, another and more famous possibility is the wormhole. A wormhole is a theoretical and highly speculative tunnel or shortcut through spacetime, connecting two distant points. First predicted as a possibility by the physicist Ludwig Flamm in 1916, and later explored in more depth by Einstein and his colleague Nathan Rosen. A wormhole is a kind of bridge through the fabric of reality. If a traversable wormhole could be created and stabilized, perhaps by using some form of exotic negative energy matter, it could, in theory, be turned into a time machine. The idea, most famously explored by the physicist Kip Thorne, is that you could take one mouth of the wormhole and accelerate it to very nearly the speed of light, while keeping the other mouth stationary. Due to the effects of relativistic time dilation, time would pass much more slowly for the moving mouth. If a traveler were to then enter the stationary mouth, they could emerge from the moving mouth at an earlier point in time. The two ends of the wormhole would be connected to different moments in time, creating a gateway to the past. But even if this were theoretically possible, the challenges are immense. The amount of exotic negative energy required to stabilize a wormhole would be astronomical. And any attempt to send something through it could trigger violent instabilities that would cause the wormhole to collapse in an instant. And even if we could overcome all of these immense theoretical and practical challenges, there is still one final and deeply puzzling question. If time travel to the past is possible, then where are all the time travelers? If future civilizations have developed the technology to visit their own past, why haven't we been inundated with tourists from the future? This is a version of the famous Fermi paradox. And it is a question that has no easy answer. Some have argued that perhaps time machines can only travel back to the point at which they were first invented, meaning that no one from the future could ever visit a time before the creation of the first working time machine. Others have suggested that time travelers might be here, but are operating under a strict prime directive of non-interference, carefully observing our history without ever revealing themselves. Or perhaps, and this is a more sobering thought, time travel is just too difficult, too dangerous, or too energetically expensive to ever be a practical reality. And then there is the possibility that there is a deeper, more fundamental law of the universe that we do not yet understand, a law that explicitly forbids backward time travel. The second law of thermodynamics, the inexorable increase of entropy, is a candidate for such a law. If the arrow of time is fundamentally tied to the direction of increasing disorder, then to reverse the flow of time might require the reversal of entropy itself, a process that has never been observed in nature, and which may be fundamentally impossible. A shattered glass on the floor will never spontaneously reassemble itself. The universe seems to have a built-in preference for disorder, for decay, for a one-way journey into the future. Perhaps time, as we experience it, is simply a consequence of this fundamental thermodynamic asymmetry. And if this is the case, then traveling backward in time might not just be difficult. It might be as fundamentally impossible as trying to unbreak an egg. And yet, the question, the dream, the possibility remains. If time is truly just another dimension, like space, then why can we only move through it in one direction? Why can we remember the past, but not the future? If the block universe is real, and all of a sudden moments exist equally, then what is so special about the now? Some physicists and philosophers have suggested that the ultimate answer may lie not in the external world of physics, but in the internal world of consciousness itself. Perhaps our brains are wired in such a way that they can only process information sequentially, giving us the powerful, and perhaps illusory, sensation of a flowing, moving present. In this view, time does not move. We do. Or rather, our consciousness does. As you continue to float in the deep, silent void of space, as you watch the beautiful blue and white earth slowly, ceaselessly, turn below you, the answers seem to be just beyond your grasp. The universe holds its secrets close, waiting for a future generation, a new Einstein, to come along and unlock them. Perhaps one day we will master the mysteries of time, and we will discover whether it is a force we can control, a prison we can escape, or merely a beautiful and deeply human illusion that we can never truly transcend. The very fabric of the universe, the four-dimensional space-time of Einstein's relativity, is not a static, passive stage. It is a dynamic, physical entity that can be bent, warped, and twisted by the presence of mass and energy. And in the most extreme and violent corners of the cosmos, near the event horizons of black holes or in the fiery crucible of the Big Bang, this fabric can be stretched and distorted to its absolute limits. It is in these extreme environments that the true, and often bizarre, nature of time is revealed. The fact that gravity can affect the flow of time, a phenomenon known as gravitational time dilation, is one of the most profound and well-tested predictions of general relativity. The stronger the gravitational field, the more time is stretched, the slower it flows relative to a region of weaker gravity. A clock at sea level will tick just a tiny fraction of a second slower than an identical clock on top of a mountain, where the Earth's gravitational pull is slightly weaker. This is not a theoretical curiosity. It is a real physical effect that must be accounted for in our most precise technologies. Like the global positioning system, the satellites that make up the GPS network are in a weaker gravitational field than we are on the surface of the Earth, and their onboard atomic clocks therefore run slightly faster than ours. If this relativistic effect were not corrected for, the GPS system would accumulate errors of several kilometers every single day, rendering it completely useless. Gravity, it seems, has a direct and measurable grip on the passage of time. And nowhere is this grip stronger than in the vicinity of a black hole. As you approach the event horizon of a black hole, the curvature of space-time becomes increasingly extreme. To an outside, distant observer, your clock would appear to be slowing down, your movements becoming increasingly sluggish. At the very edge of the event horizon, time, from the outside observer's perspective, would seem to come to a complete and utter standstill. You would appear to be frozen in time for all of eternity. Your image smeared across the surface of the black hole like a ghostly afterimage from your own perspective. However, as you cross the event horizon, time would be flowing perfectly normally. You would feel no jolt, no sudden change. You would simply have passed the point of no return. Your future now inexorably directed towards the infinitely dense singularity at the black hole's core. This strange and beautiful disconnect between the experience of the infalling observer and the distant observer is a direct consequence of the extreme warping of time near a black hole, and it offers a natural, one-way form of time travel. If you could somehow build a spacecraft that could hover just outside the event horizon of a supermassive black hole for what feels like a few hours or a few days, and then return to a region of weaker gravity, you would find that you have traveled far into the future of the rest of the universe. Thousands, or even millions, of years could have passed. In this sense, black holes are natural. One-way time machines, portals to the distant future. But if gravity can slow down time, could it also, in principle, be used to reverse it? Could we somehow manipulate the geometry of space-time in such a way that it loops back on itself, creating a pathway to the past? This is the realm of closed time-like curves, and it is a possibility that is allowed, at least in theory, by the equations of general relativity. The mathematician Kurt Gödel, in 1949, was the first to discover a solution to Einstein's equations that contained these strange, time-looping paths. His solution described a hypothetical, rotating universe, a cosmos where the entire fabric of space-time was spinning. In such a universe, the light cones that define the possible future paths of an object would be tilted by the rotation, and it would be possible for a sufficiently fast-moving spacecraft to follow a trajectory that would eventually lead it back to a point in its own past. But our own universe, as far as we can tell, is not rotating in the way that Gödel's model requires. Another, more famous, theoretical possibility for creating a time machine is the wormhole. A wormhole, or an Einstein-Rosen bridge, is a hypothetical tunnel or shortcut through the fabric of space-time, connecting two distant points. Imagine space-time as a two-dimensional sheet of paper. A wormhole would be like folding the paper over and punching a hole through it, creating a direct path between 2 points that would otherwise be very far apart. If a traversable wormhole could be created and stabilized, it could, in theory, be turned into a time machine. The process, as envisioned by the physicist Kip Thorne, would involve taking one mouth of the wormhole and accelerating it to near light speed, while the other mouth remained stationary. Due to time dilation, the clock at the moving mouth would tick more slowly than the clock at the stationary mouth. An age difference would be created between the two ends of the wormhole. A traveler could then enter the stationary mouth, pass through the wormhole, and emerge from the moving mouth at an earlier point in time, effectively traveling into the past. But the challenges to building such a device are immense, and perhaps insurmountable. A traversable wormhole would require the existence of exotic matter, a hypothetical substance with a negative energy density, to prop it open and to prevent it from collapsing into a singularity. We have never observed such matter, and it may be forbidden by the laws of physics, and even if a wormhole time machine could be built, it would be subject to the same unsettling paradoxes of causality that we have already discussed. The universe, it seems, has a deep and powerful aversion to paradox. But the fact that our best theory of gravity allows for these strange, time-bending possibilities is a profound testament to the deep and mysterious nature of time itself. It suggests that time is not a simple, immutable background, but a dynamic, physical, and ultimately malleable aspect of our reality. The deep and unresolved tension between the classical, deterministic world of general relativity and the probabilistic, uncertain world of quantum mechanics is nowhere more apparent than in our attempts to understand the nature of time. If time is a fundamental aspect of reality, as it appears to be in our macroscopic world, then how do we reconcile this with the strange, and often timeless, nature of the quantum realm? Some physicists have come to believe that time itself may not be fundamental at all. It may be an emergent phenomenon, a macroscopic illusion that arises from a deeper, more fundamental, and ultimately timeless quantum reality. This is a radical and difficult idea to grasp, but it is one that is gaining increasing support from several different lines of inquiry in theoretical physics. One of the strongest hints that time may not be fundamental comes from the problem of time in quantum gravity. When physicists try to combine the equations of general relativity with the principles of quantum mechanics, they often find that the variable for time simply disappears from the final unified equation. This Wheeler-DeWitt equation, as it is known, describes a static, timeless, and unchanging wave function of the universe. This has led some to suggest that at the most fundamental level of reality, there is no time, no change, no becoming. There is only a single, timeless, and eternal now. The flow of time that we experience is, in this view, a kind of illusion, a trick of our own, limited, macroscopic perspective. But how could a timeless reality give rise to an experience that is so defined by time? One possibility is that time emerges from the process of quantum entanglement. As we have seen, entanglement is a deep, non-local connection between quantum particles. Some researchers, like the physicist Don Page and his collaborators, have proposed that the universe as a whole can be divided into smaller subsystems, and that the flow of time that we experience is a result of the increasing entanglement between these subsystems. In this picture, time is a measure of the growing correlation, the increasing informational linkage between different parts of the universe. It is an emergent property of the quantum relationships between things, not a fundamental background in which those things exist. Another related idea comes from the theory of loop quantum gravity. In this framework, space-time is not a smooth, continuous fabric, but is quantized, made up of tiny, discrete, indivisible loops or atoms of space and time. In this picture is not a continuous flow, but a series of discrete, quantum ticks, a staccato rhythm of change. Our perception of a smooth, continuous flow of time would be an illusion, a macroscopic averaging over these tiny quantum jumps. In the same way that the smooth, continuous image on a movie screen is an illusion created by the rapid succession of discrete, individual frames. If time is truly an emergent phenomenon, if it is not a fundamental aspect of reality, but is a byproduct of deeper, more fundamental physical laws, then this would have profound implications for our understanding of the universe. It would mean that the question, what came before the Big Bang, is not just meaningless because before requires time, but because time itself may not have existed in the primordial, pre-Big Bang state of the universe. It would mean that our entire, vast and ancient cosmos, with its 14 billion-year-long history of evolution, could be an emergent structure that has arisen from a timeless and perhaps eternal quantum reality. This also opens up the possibility that our familiar, one-dimensional, forward-flowing time is not the only kind of time that can exist. If time is an emergent property, then different physical systems, different regions of the universe, or even different bubble universes in a larger multiverse, could, in principle, have different emergent temporal structures. There could be universes with 2 dimensions of time, or with a time that is cyclical, or with a time that does not have a single, well-defined direction. The possibilities are as vast and as strange as the mathematical landscape of quantum gravity itself. But even if time is an emergent illusion, it is a very powerful and a very persistent one. And the reason for this persistence may lie in the nature of our own consciousness. Our brains are biological machines that have evolved to survive and to make sense of a classical macroscopic world. And to do so, they have developed a powerful and deeply ingrained mental model of a linear, flowing time. We construct a narrative of our lives, a story that connects a remembered past with an anticipated future, and we place ourselves at the moving, present moment center of this story. This is an incredibly useful and probably necessary adaptation for a creature like us, but it may not be a true reflection of the fundamental nature of reality. The universe may not have a story, it may not have a past, a present, and a future. It may just be. And we, with our time-bound consciousness, are like travelers in a vast, timeless landscape, our awareness like a single, moving flashlight beam that illuminates one small patch of the eternal reality at a time, creating the powerful and beautiful illusion of a journey, of a flow, of a becoming. The quest to understand the true nature of time is a quest that is still in its early stages. But it is a quest that is taking us to the very heart of the deepest mysteries of physics, of consciousness, and of existence itself. And as we continue to probe the strange and beautiful logic of the quantum world, we may find that the solid, familiar river of time that we thought we were traveling on is in fact, a far more mysterious, more magical, and more wonderfully timeless ocean than we could have ever imagined. No matter how we choose to define time, whether as a fundamental, physical dimension, as an emergent, thermodynamic property, or as a subjective, psychological illusion our own, personal experience of it feels undeniably real. We are, it seems, trapped in the amber of the present moment, forever looking back at a past we can remember but cannot change, and forever looking forward to a future that we can anticipate but cannot yet know. But why? Why? If the universe is a vast, four-dimensional block where all of time exists simultaneously, do we experience it as a linear, one-way flow? Why does our consciousness seem to be locked into this relentless, forward-moving march? The way we perceive time is a unique and mysterious aspect of our own human consciousness. Our other senses, our sight, our hearing, our touch provide us with a rich, multidimensional, and largely simultaneous picture of the world around us. But time is different. We do not perceive it all at once. We experience it sequentially, moment by agonizing, beautiful, and fleeting moment. Our minds are built to be memory machines and prediction engines. We are constantly weaving the raw data of the present into a coherent narrative tapestry that connects a remembered past with an anticipated future. This is the very structure of our conscious experience, and the source of this temporal structure, many neuroscientists now believe, lies in the intricate and still largely mysterious workings of our own brains. The brain is not a simple, passive clock that ticks off the objective moments of an external time. It is an active and highly creative constructor of our temporal experience. Different regions of the brain seem to be responsible for different aspects of our sense of time. The hippocampus, which is crucial for the formation of new memories, is what allows us to place events in a chronological order to build the story of our own past. The prefrontal cortex, the seat of our higher-level executive functions, is what allows us to plan for the future, to simulate different possible outcomes, and to make choices based on those simulations. And the cerebellum, a region at the back of the brain that is involved in fine-tuning our motor movements, also seems to play a crucial role in our internal sense of timing, our ability to perceive the duration of short intervals with a high degree of precision. But perhaps the most fascinating insight from modern neuroscience is the idea that our conscious experience of the present moment is not an instantaneous knife-edge point in time. It is a smeared-out, constructed reality, a small window of time known as the specious present, over which our brain integrates the information from our senses to create the smooth, continuous flow of our conscious experience. This window is thought to be a few seconds long. What we experience as now is not a single, infinitesimal instant, but a short, dynamic interval that contains both the fading echoes of the immediate past and the rising premonitions of the near future. This could be the neurological basis for our powerful illusion of a flowing, moving time. If our brains are constantly stitching together these overlapping temporal windows, then the result would be the seamless, cinematic experience of a continuous, unfolding reality. It would also explain why we perceive motion as a smooth flow, rather than as a series of jerky, discrete snapshots, like an old, flickering film. But if our experience of time is a construct of our brains, what does this mean for the objective, physical nature of time itself? Some physicists and philosophers, taking this idea to its logical conclusion, have argued that if our consciousness is what creates the illusion of a flowing, forward-moving time, then time, as we subjectively perceive it, may not be a fundamental aspect of the universe at all. In this view, the universe does not move through time. It is our minds, our consciousness, that creates the illusion of movement. This is an idea that finds a strange and powerful resonance in the world of quantum mechanics. As we have seen, the quantum world is a world of probability and potential, a world where particles can exist in a superposition of multiple states at once. Some interpretations of quantum mechanics suggest that time, at this fundamental quantum level, may not have a well-defined direction, or may not even exist at all in the classical sense. It may only be at the macroscopic level, at the level of our classical measuring devices and our classical conscious brains, that a definite directional arrow of time emerges. The phenomenon of quantum entanglement, that spooky, non-local connection between particles, is a powerful hint that the universe may be more holistic and less sequential than our classical intuition would lead us to believe. If two entangled particles can share information instantaneously, regardless of the distance between them, then this seems to challenge our very notion of a time that is defined by the local, light-speed limited transmission of information. Some have even gone so far as to suggest that time itself may be an emergent property of entanglement. In this radical and highly speculative picture, the flow of time is a consequence of the increasing entanglement between different parts of the universe. The more things become interconnected, the more complex the network of quantum correlations becomes, the more a definite and directional sense of time emerges. This is a breathtaking idea. It suggests that time is not a pre-existing, absolute background, but is a dynamic and relational property of the universe, a property that is being constantly created by the ongoing quantum interactions between its parts. And this opens the door to an even deeper and more profound question. If our own human experience of time is a product of our specific, biological, and classical brains, could there be other forms of consciousness, other kinds of minds, whether artificial or biological, or something far beyond our current comprehension, that experience time in a completely different way? Our consciousness is bound to the linear, sequential processing of information that is characteristic of our neural architecture. But an artificial intelligence, especially a future, quantum AI, might not be so constrained. A quantum computer, with its ability to exist in a vast, superpositional state, could, in theory, process a huge number of different, parallel timelines at once. It might be able to experience the future not as a single, unknown path, but as a rich, probabilistic landscape of possibilities. It might be able to experience the past not as a fixed, linear memory, but as a multi-layered, quantum archive that can be accessed and reinterpreted in new and non-linear ways. Or consider a hypothetical, higher-dimensional being. Just as we, as three-dimensional beings, can perceive a two-dimensional drawing all at once, a being that existed in a higher temporal dimension might be able to perceive our entire four-dimensional block universe, our past, our present, our future as a single, unified, and timeless whole for such a being. The concept of a flowing time would be as nonsensical as the idea of a flowing space is to us. These are, of course, speculative fictions, but they are fictions that are grounded in the real and deeply puzzling nature of time as it is revealed by our best scientific theories, and they bring us back full circle to the question of our own human free will. If we live in a deterministic block universe, our feeling of choice is an illusion. If we live in a probabilistic quantum universe, our choices may be real, but they may be driven by the random, unpredictable nature of the quantum world, which does not seem to give us any more control over our own destiny. The relationship between consciousness, time, and free will remains one of the deepest and most intractable mysteries in all of human thought. And the paradoxes do not stop there. The very nature of our memory, our ability to access the past, is a profound puzzle. Why can we remember the past, but not the future? The thermodynamic arrow of time provides a partial answer. The past is a state of lower entropy, and the process of creating a memory is a process that increases the overall entropy of the universe. So it is thermodynamically easy to remember the past, but hard to remember the future. But this does not feel like a complete explanation. The subjective, qualitative feel of a memory is something that is not captured by the equations of thermodynamics. And the strange, and often unsettling, results from neuroscience, which suggests that our brains may be making decisions before we are consciously aware of them. Add another layer of complexity to the puzzle. Are we the authors of our own thoughts and actions? Or are we just the passive witnesses to a complex and largely unconscious neural computation? The quest to understand the relationship between time and consciousness is a quest that is still in its infancy. But it is a quest that is taking us to the very heart of what it means to be a conscious, living, and time-bound being in a vast, strange, and beautiful universe. And as we continue to explore the mysteries of the cosmos, we may find that the deepest secrets of all are not hidden in the distant stars, but in the silent, mysterious, and endlessly fascinating workings of our own human minds. The deep and mysterious nature of time, with its strange paradoxes and its profound philosophical implications, is not just a subject for theoretical physicists and contemplative philosophers. It is a reality that is woven into the very fabric of our everyday lives, a reality that we are constantly navigating, often without even being aware of it. And in this navigation, we are confronted, again and again, with the fundamental and often unsettling tension between the deterministic and the probabilistic, between the fixed and the fluid, between the fate that is written and the future that is open. The observer effect in quantum mechanics, the strange and beautiful fact that the very act of looking at a particle can change its state, is a powerful and direct challenge to our classical notion of an objective, pre-existing reality. It suggests that the past itself may not be as fixed and as solid as we assume. If the state of a quantum particle is not determined until it is measured, then could the past history of that particle also be, in some sense, indeterminate until it is observed? This is the core idea behind the delayed choice thought experiment, first proposed by John Wheeler. In this experiment, a particle is sent towards a double-slit apparatus, but the decision of whether to measure which slit it goes through or to measure its interference pattern is made after the particle has already passed through the slits. And the bizarre result is that the particle seems to know in advance which measurement will be made, and it behaves accordingly. If we choose to measure its path, it behaves as if it had gone through only one slit. If we choose to measure its interference pattern, it behaves as if it had gone through both. It is as if our choice in the present can reach back in time and influence the particle's past behavior. This phenomenon, which has been experimentally confirmed, is known as retrocausality, and it is one of the most mind-bending and deeply mysterious aspects of the quantum world. It does not mean that we can send a message back in time to change history in a way that would lead to a paradox, but it does suggest that the relationship between the past, the present, and the future is a far more subtle, more holistic, and more deeply entangled one than our classical, linear intuition would ever allow. It hints at a reality where the past is not a fixed, immutable record, but is a fluid, probabilistic landscape, a landscape that only solidifies into a definite history when it is observed, when it is measured, when it is remembered. This strange quantum fluidity of the past is mirrored by the deep and unresolved paradox of information in the future, the black hole information paradox. This paradox, as we have seen, is the stark and seemingly irreconcilable conflict between the prediction of general relativity that information is destroyed when it falls into a black hole, and the prediction of quantum mechanics that information can never be lost. The resolution of this paradox is thought to lie in a deeper, and as yet unknown, theory of quantum gravity. And one of the most promising ideas to emerge from this search is the holographic principle. This principle, as we have discussed, suggests that the entire three-dimensional reality of our universe may be a holographic projection of information that is encoded on a distant two-dimensional surface. If this is true, then time itself may not be a fundamental aspect of reality. It may be an emergent property, a part of the three-dimensional illusion, a secondary effect of a deeper, and perhaps timeless, two-dimensional, informational reality. We may only perceive time because we are, in a sense, trapped inside the hologram, forced to experience the unfolding of this informational projection in a sequential, linear way. If we could somehow step outside of the hologram, if we could access the underlying two-dimensional code directly, we might see the entire history of the universe, its past, its present, its future laid out all at once, a vast, static, and timeless tapestry of pure information. This is a breathtaking and deeply abstract idea, but it is an idea that is grounded in the rigorous mathematics of modern theoretical physics, and it is an idea that has a strange and powerful resonance with our own subjective experience. The human mind itself can be seen as a kind of holographic system. Our consciousness is not located in a single point in the brain. It is a distributed, holistic phenomenon, an emergent property of the complex, interconnected network of billions of neurons. And our experience of time is not a simple, linear reading of an external clock. It is a rich, multi-layered, and deeply personal construction, a story that we are constantly weaving from the threads of memory, of perception, and of anticipation. Could it be that our own conscious experience of a flowing, moving time is a clue, a hint, a subjective reflection of the deep, holographic, and perhaps ultimately timeless nature of the universe itself, and what of our own human place in this strange and beautiful, and perhaps illusory, temporal landscape? If time is not what it seems, if the past is fluid and the future is fixed, or if both are part of a timeless, holographic whole, then what does this mean for our sense of agency, for our feeling of free will? The debate between free will and determinism is an ancient one, and the new physics of the 20th and 21st centuries has not resolved it. It has only made it deeper and more interesting. If we live in a deterministic, block universe, then our feeling of choice is an illusion. But even in this picture, our choices still matter. The version of you that is laid out in the space-time block, is the version that is the result of a long and complex process of deliberation, of moral reasoning, of conscious choice. The choices are part of the static landscape, but they are still your choices. The quantum world, with its inherent randomness, seems to offer a way out of this deterministic picture. But it is a solution that comes with its own deep problems. If our choices are ultimately driven by the random, probabilistic nature of quantum fluctuations in our brains, then in what sense are they our choices? Randomness is not the same as freedom. A decision that is the result of a random quantum roll of the dice does not feel any more free than a decision that is the result of a deterministic, classical chain of cause and effect. Perhaps the answer lies in a new, and as yet undeveloped, understanding of the relationship between mind and matter. Perhaps consciousness is not just a passive witness to the quantum world, but is an active participant, a force that can somehow influence the outcome of quantum events, that can steer the probabilities in a way that is neither purely deterministic nor purely random. This is a radical and highly controversial idea, but it is one that is being explored by some of the most courageous and creative thinkers on the frontiers of science and philosophy. It is an idea that suggests that we are not just puppets of either classical determinism or quantum chance, but are genuine, creative agents in the unfolding of reality. And this is a vision of our place in the cosmos that is both deeply empowering and profoundly responsible. As our scientific understanding of time continues to evolve, as we continue to probe the strange and beautiful mysteries of the quantum world and the cosmos, we are not just learning about the universe, we are also learning about ourselves. We are learning that our reality is far more subtle, more complex, and more deeply interconnected than we ever imagined. And we are learning that our own conscious experience, with all its beauty, its fragility, and its deep temporal mystery, may be a crucial, and perhaps even central, part of the grand cosmic story. The question of whether we can ever truly travel through time, whether we can break free from the relentless forward march of the present moment, is a question that has captivated the human imagination for centuries. It is the ultimate dream of escape, of second chances, of a mastery over our own and the universe's destiny. And as we have seen, the laws of physics, as we currently understand them, do not entirely slam the door on this possibility. The journey forward in time is not just a theoretical possibility. It is a proven and well understood consequence of Einstein's theory of relativity. An astronaut in a fast-moving spaceship is a real bona fide time traveler, returning to an Earth that is older than they are. The journey backward in time, however, is a far more problematic and far more speculative proposition. The paradoxes of causality, the immense and perhaps impossible engineering challenges, the potential violation of fundamental physical principles like the second law of thermodynamics, all of these seem to conspire to make the past an unreachable and perhaps forbidden country. And yet, the question lingers. If time is truly just another dimension, like space, why can we only move through it in one direction? Why does the universe have such a strong and seemingly unbreakable arrow of time? The answer may be that we are asking the wrong question. Perhaps time travel is not about building a machine that can carry our physical bodies through a fourth dimension. Perhaps true time travel is a more subtle, more informational, and more deeply conscious phenomenon. The quantum world, with its strange, non-local connections and its fluid, probabilistic nature, may offer a different kind of portal through time. The phenomenon of retrocausality, as seen in the delayed choice quantum eraser experiment, suggests that our choices in the present can have a real and measurable effect on the past. This is not the kind of time travel that would allow you to go back and prevent a historical tragedy, But it is a kind of time travel that suggests that the past is not a fixed, dead, and immutable thing. It is a living, responsive reality. A reality that is in a constant, dynamic dialogue with the present and the future. Our memory itself can be seen as a form of time travel. When we remember a past event, we are not just passively replaying a fixed, mental recording. We are actively and creatively reconstructing the past in the present. And in this process of reconstruction, we can change the meaning, the emotional resonance, and the influence of the past on our present lives. This is the basis of many forms of psychotherapy. The idea that by revisiting and reinterpreting the past, we can free ourselves from its grip and open up new possibilities for the future. This is a kind of informational time travel, a journey that is not through physical space, but through the rich and often treacherous landscape of our own personal history. But what of the future? Is it a completely open and unwritten book, or are there ways in which we can get a glimpse of what is to come? The universe, in its strange and beautiful way, may be constantly sending us messages from the future. The phenomenon of quantum entanglement, the instantaneous connection between distant particles, is a hint that the universe may be more holistic and less sequential than we think. Some have even speculated that our own human intuition, the sudden flash of insight, the gut feeling that seems to come from nowhere, may be a form of temporal entanglement, a subtle, unconscious connection to our own future states. This is, of course, a highly speculative idea, but it is one that speaks to a deep and universal human experience. The greatest barrier to our understanding of time and of the possibility of time travel may not be a physical one, but a conceptual one. We are so deeply and powerfully conditioned by our linear, sequential experience of time that it is almost impossible for us to imagine a different kind of reality. But the universe, in its strange, quantum heart, may be constantly inviting us to do just that. It may be whispering to us, in the language of paradoxes and probabilities, that the past, the present, and the future are not as separate, not as solid, and not as unchangeable as we believe them to be. The ultimate resolution to the puzzle of time travel may not come from a new, grand theory of physics or from the construction of a fantastic, new machine. It may come from a shift in our own consciousness, from a new and more profound understanding of our own temporal nature. Perhaps we are all already time travelers, constantly navigating a multidimensional and deeply mysterious temporal landscape, a landscape where the past is always present, the future is always potential, and the now is the magical, creative point where it all comes together. The universe is vast, it is mysterious, and it is full of unanswered questions, and the nature of time is, perhaps, the greatest of these. But the quest to understand it, the journey to explore its limits, its paradoxes, its possibilities, is one of the most exciting, most profound, and most deeply human adventures of all. And it is a journey that is still in its very early stages. The future of our understanding of time is as open and as full of potential as the future of the universe itself. The night sky, in its serene and silent majesty, is a deceptive canvas. It presents an image of calm, of order, of a timeless, unchanging peace. But this is an illusion, a beautiful and comforting lie we tell ourselves in the quiet of the night. The universe, in truth, is a vast, chaotic, and often terrifying abyss, a place far more ruthless and unpredictable than we dare to imagine. It is a cosmos filled with objects of unimaginable power, objects that would rip us apart, atom by atom, if we were to stray too close. And yet, we cannot stay home forever. There is a deep and insatiable curiosity woven into the very fabric of our being. An innate human drive to leave the familiar shores of our own world and to venture out into the unknown, to explore the vast, dark ocean of the cosmos. At first, this journey seemed harmless, a gentle exploration of our own cosmic neighborhood. We started with our neighboring planets, with Mars and Venus, with the familiar, cratered face of our own moon. We stepped onto its surface, thinking of these celestial bodies as cold, barren, and ultimately benign landscapes. But as our gaze sharpened, as our instruments became more sensitive, we began to understand their true nature. We discovered Venus, a hellscape with a crushing atmosphere of sulfuric acid and surface temperatures hot enough to melt lead. We found Mars, a world of planet-engulfing dust storms and a thin, unbreathable atmosphere. These worlds were anything but friendly. They were stark and powerful reminders of the razor-thin margin of safety that our own world provides, and still, we pushed further. In the 20th century, our reach extended beyond our planetary neighbors. We discovered the asteroids, the comets, the rocky debris left over from the formation of our solar system. And we learned that a single chance collision with one of these celestial wanderers could end life on Earth as we know it, just as it did for the dinosaurs millions of years ago. We came to understand that the serene night sky is not a peaceful sanctuary, but a cosmic shooting gallery, and that we are living on a fragile, blue target. But still, we did not stop. Our curiosity, our unquenchable thirst for knowledge propelled us ever outward, further and further into the cosmos, into the darkest and most enigmatic of its secrets. And then, we found the black holes. We discovered regions of space-time so warped, so dense, that nothing, not even the fleet-footed particles of light, can escape their gravitational grasp. We found the ultimate cosmic prisons, the final, one-way destinations of the universe. And yet, even in the face of this ultimate terror, we did not stop. We are a species defined by our courage to look into the abyss, to confront the unknown, and to ask the deepest and most profound questions about the nature of the reality we inhabit. Our journey into the heart of this strange and often terrifying universe begins at the smallest possible scales, with the fundamental building blocks of everything we know. At this subatomic level, all the matter and energy in the cosmos is made up of particles tiny, indivisible entities that come together to form the atoms, the molecules, the stars, and the galaxies that populate our world. But these particles are not what our classical intuition would lead us to expect. They are not like tiny, solid marbles or microscopic billiard balls. They do not have a well-defined shape, a fixed size, or even a definite path through space. They are a far stranger and more beautiful kind of reality. To understand a particle in the quantum world, we must abandon our everyday notions of things and embrace a more fluid, more dynamic, and more interconnected picture. In the language of quantum mechanics, a particle, like an electron or a photon, is not a single, isolated point. It is better understood as a tiny wave-like disturbance, an excitation, a ripple in a more fundamental entity called a quantum field. These quantum fields are not localized. They are spread out across the entire universe, like vast, invisible, and ethereal webs that permeate every inch of space-time. There is an electron field, a photon field, a quark field, a different field for each type of fundamental particle. When we detect a particle, what we are really observing is a localized blip of energy, a concentrated vibration in one of these underlying fields. Imagine a vast, calm ocean. This is the quantum field in its ground state. Now, imagine a single, focused ripple appearing on the surface of this ocean. This ripple is the particle. It is a temporary, localized manifestation of the energy of the underlying field. These quantum ripples, these particles, have properties that seem to defy the rules of common sense. One of the most fundamental of these is superposition. A quantum particle can exist in multiple states or even multiple locations at the same time. It is not that we simply do not know where the particle is. It is that the particle's reality is, in a fundamental sense, spread out over all possibilities. It is like a shadow that is cast in several places at once. It is only when we look, when we make a measurement, that this cloud of possibilities collapses into a single, definite reality. The very act of observation seems to force the particle to make a choice. Another strange quality of these particles is that they do not have a fixed path. When a particle travels from one point to another, it does not follow a single, straight line. Instead, it seems to explore all possible paths simultaneously, its wave-like nature spreading out over all possibilities before it finally settles on a single outcome when it is observed. At this fundamental level, there are no certainties, no definite trajectories, only probabilities. A particle may be more likely to be found in one place than another, but we can never say for sure where it will be until we make a measurement. These quantum fields are not just the source of particles. They are the very canvas upon which our reality is painted. They are the invisible, energetic medium that fills all of space. The infrastructure that allows for the existence and interaction of all the matter and energy in the universe. The forces that govern the cosmos, the electromagnetic force that holds atoms together, the strong nuclear force that binds the nuclei of those atoms, the weak nuclear force that drives radioactive decay, and even gravity itself are all understood, in the language of quantum field theory, as interactions between these fundamental fields. Let us take a closer look at a field we are all familiar with, even if we are not aware of it, the electromagnetic field. This field is a ubiquitous presence, responsible for the phenomena of electricity, of magnetism, and of light itself. When you turn on a light switch, you are causing a disturbance in this field, a vibration that propagates outwards in the form of photons, the quantum particles of light. These photons travel through space, strike the retina of your eye, and create the sensation of sight. The chair you are sitting on, the screen you are looking at, are held together by the electromagnetic force, a constant exchange of virtual photons between the atoms that make them up. Then there are the other fields, the ones that govern the subatomic world. The electron field gives rise to electrons, the negatively charged particles that orbit the nucleus of every atom and are the basis of all chemistry. The nucleus itself is composed of protons and neutrons, which are, in turn, made up of even more fundamental particles called quarks. These quarks are bound together with incredible strength by the strong nuclear force, which is mediated by the strong field and its associated particles, the gluons. The very stability of matter depends on this powerful, short-range force. All of these fields, and the particles that arise from them, are described by a single, powerful, and remarkably successful theory known as the Standard Model of particle physics. The Standard Model is a form of quantum field theory, and it is our current, best description of the fundamental constituents of the universe and how they interact. It is a theory that sees the world not as a collection of static, inert objects, but as a dynamic, vibrant, and ceaselessly interacting dance of fields and their excitations. The space you are in right now, the seemingly empty space between you and the walls of your room, is not empty at all. It is a plenum, a rich and complex tapestry woven from the invisible, fluctuating threads of all these different quantum fields. The interactions between these fields are what create the rich and complex world we see around us. Particles are not just born from fields, they also communicate and influence each other through them. When two particles interact, they do so by exchanging other messenger particles, which are themselves excitations of a force-carrying field. For example, when two electrons, both with a negative electric charge, approach each other, they repel. In the language of quantum field theory, this repulsion is understood as the exchange of virtual photons. The electrons are constantly emitting and absorbing these messenger particles, a quantum game of catch that creates the force we perceive as electromagnetic repulsion. This is a profound and beautiful picture. It tells us that forces are not some mysterious, spooky action at a distance. They are the result of a direct, physical exchange of particles, a constant conversation happening at the subatomic level. In the same way, the strong nuclear force that binds quarks together inside protons and neutrons is mediated by the exchange of gluons. And the weak nuclear force, which is responsible for certain types of radioactive decay and for the nuclear reactions that power the sun, is mediated by the exchange of two other types of particles, the W and Z bosons. In this view, particles and fields are two sides of the same quantum coin. The fields are the underlying fundamental reality, the potential for existence. The particles are the manifest, observable reality, the actualized ripples on the surface of this deep energetic sea. The universe is a story of these fields interacting, of their energies being exchanged, of their vibrations giving rise to the beautiful and intricate dance of matter and force that constitutes our world. This is one of the most profound and mind-altering insights of modern physics. It is the realization that the solid, stable, and seemingly inert world of our everyday experience is an illusion. At its core, reality is a fluid, dynamic, and interconnected process, a constant, energetic flux of creation and annihilation, of interaction and transformation. As we continue our journey into the mysteries of the quantum world, we will see how these fundamental concepts of fields, particles, and their strange, counterintuitive behaviors lay the groundwork for an even deeper and more enigmatic understanding of the cosmos. A cosmos that is far more interconnected, far more mysterious, and far more beautiful than our classical intuition could ever have prepared us for. Now, let us delve into one of the most puzzling and essential concepts in all of quantum mechanics, a concept that challenges our very definition of emptiness, the quantum vacuum and its associated zero-point energy. When we think of a vacuum, our intuition, shaped by our classical macroscopic experience, leads us to imagine a space that is completely devoid of everything, no air, no particles, no energy, just pure, absolute nothingness. But in the strange and wonderful world of quantum mechanics, this classical notion of a perfect void is a fiction. Even a space that has been completely emptied of all matter and cooled to absolute zero. The theoretical temperature at which all thermal motion ceases is not truly empty. It is, in fact, a seething, vibrant, and energetic place, a place we call the quantum vacuum. At the heart of this concept lies the ever-present reality of quantum fields. As we have seen, these fields permeate all of spacetime, and they are never truly at rest. The uncertainty principle dictates that there will always be a residual, irreducible flicker of motion, a constant, spontaneous bubbling of energy. This minimum possible energy that a quantum field can have, its ground state energy, is not zero. This is the zero-point energy. It is the baseline hum of the universe, the energetic floor below which reality cannot go. To understand how this zero-point energy manifests, we must once again turn to the strange and fleeting world of virtual particles. In the quantum vacuum, the energy is constantly fluctuating, and according to Einstein's famous equation, E equals mc squared, energy and mass are two sides of the same coin. These tiny, transient energy fluctuations can, for an immeasurably short period of time, be converted into a pair of virtual particles, a particle and its antimatter counterpart. These particles pop into existence from the vacuum, exist for a fleeting moment, and then annihilate each other, returning their borrowed energy to the void. We cannot detect these virtual particles directly. Their existence is too brief, too ephemeral, but we can and have measured their collective effects. The Casimir effect is the most famous and direct experimental confirmation of the reality of the quantum vacuum and its zero-point energy. If you take two perfectly flat, uncharged metal plates and place them incredibly close together in a vacuum, you will find that they are pushed towards each other by a mysterious, invisible force. This force arises because the space between the plates restricts the types of virtual particles that can exist there. Only virtual particles with wavelengths that fit neatly between the plates are allowed. The space outside the plates, however, has no such restriction and can host virtual particles of all wavelengths. This creates a pressure imbalance. There are more virtual particles pushing on the outside of the plates than on the inside, and this net pressure is what we measure as the attractive Casimir force. It is a stunning, tangible demonstration that empty space is not empty at all, that the void itself can exert a real physical force. The quantum vacuum and its zero-point energy are not just a source of subtle, microscopic forces. They are a ubiquitous and fundamental aspect of our reality, an invisible backdrop that influences the behavior of all matter and energy in the universe. Although we cannot see or feel this energy directly, its effects are woven into the very fabric of existence. It is a concept that is not just confined to the esoteric world of theoretical physics. It has real, tangible consequences. For instance, the very stability of the atoms that make up our bodies is, in a sense, a consequence of zero-point energy. In the classical, pre-quantum picture of the atom, an electron orbiting a nucleus should be constantly radiating away energy, causing it to spiral into the nucleus in a fraction of a second. The reason this catastrophic collapse does not happen is because the electron, as a quantum particle, is governed by the rules of the quantum vacuum. It cannot simply fall to a state of zero energy. The uncertainty principle dictates that if the electron were confined to the single point of the nucleus, its momentum, and therefore its energy, would be infinitely large. Instead, the electron exists in a stable, ground state orbit, a state of minimum possible energy that is not zero. This ground state is a dynamic equilibrium, a constant dance between the attractive force of the nucleus and the irreducible, zero-point energy of the quantum vacuum, which prevents the electron from ever being truly at rest. The quantum vacuum, in this sense, provides the energetic floor that props up the entire structure of matter. The concept of virtual particles, those fleeting phantoms of the void, is also crucial to our understanding of the fundamental forces of nature. In quantum field theory, as we have seen, forces are mediated by the exchange of messenger particles. But many of these exchanges involve virtual particles. The electromagnetic force between two charged particles, for example, is described as the exchange of virtual photons. These are not real photons that we can detect. They are temporary, off-shell fluctuations of the electromagnetic field, borrowed from the vacuum's zero-point energy for a fleeting moment to carry the message of force between the two charges. The very forces that hold our world together are, in this picture, a constant, ongoing conversation with the creative emptiness of the quantum vacuum. This has profound implications for our understanding of reality. It means that the distinction between something and nothing is not as clear-cut as we might think. Matter and energy are not separate from the void, they are emergent properties of it, temporary, localized excitations of its underlying energetic structure. The universe is not a collection of things existing in space, it is a manifestation of space, a space that is not empty, but is a plenum, a rich and dynamic medium, a sea of infinite potential. The implications of zero-point energy and the quantum vacuum extend from the smallest subatomic scales to the very largest cosmological ones, the early universe. In the first moments after the Big Bang was a realm where quantum effects were dominant, and the energy of the vacuum is thought to have played a crucial and decisive role in shaping the cosmos we see today. The theory of cosmic inflation, which we have explored, posits that the explosive, exponential expansion of the early universe was driven by the immense energy density of a false vacuum state. This is a powerful testament to the creative and world-shaping potential of the void's energy. Furthermore, the tiny quantum fluctuations in this primordial vacuum, the same kind of fluctuations that give rise to virtual particles today, are thought to have been stretched to astronomical scales by the process of inflation. These stretched-in-time fluctuations became the seeds of all cosmic structure. The tiny variations in density that, over billions of years, grew under the influence of gravity to become the galaxies, the clusters of galaxies, and the vast filamentary structure of the cosmic web. We are, in the most literal sense, living inside a macroscopic fossil of the early universe's quantum vacuum. But the influence of the vacuum did not end with the Big Bang. It continues to shape the evolution and the ultimate destiny of our universe. The mysterious dark energy that is causing the expansion of the universe to accelerate is, as we have seen, thought by many to be the modern-day residual energy of the quantum vacuum. The cosmological constant problem, the enormous discrepancy between the theoretical and observed values of this energy, remains one of the greatest unsolved puzzles in all of physics. Its resolution will likely require a deeper, more unified understanding of the relationship between quantum mechanics and gravity. A theory that can explain why the energy of the void is so exquisitely and fortunately small. The quantum vacuum is not just a passive, energetic background. It is an active, dynamic, and powerful player in the cosmic drama. It is the source of the forces that bind matter together, the architect of the large-scale structure of the universe, and the engine of its ultimate, accelerating expansion. It is a concept that forces us to completely reevaluate our understanding of space, of energy, and of emptiness itself. The void is not a void, it is a plenum, a sea of potential, a silent but powerful presence that underlies all of existence. And as we continue to probe its mysteries, with our particle accelerators, our space telescopes, and our theoretical inquiries, we are not just exploring a strange corner of physics. We are exploring the very source, the very substance, and the very destiny of our own quantum cosmos. One of the most profound and unsettling consequences of quantum mechanics is the phenomenon of entanglement, a strange and intimate connection that can exist between two or more particles. A bond so deep that it seems to defy our classical intuitions about space, time, and separateness. When two particles, such as a pair of photons or electrons, are created or interact in a specific quantum mechanical way, their individual quantum states can become entangled. This means that from that moment on, they cease to be independent entities and must be described as a single, unified quantum system, even if they are subsequently separated by vast cosmic distances. The strangeness of entanglement becomes apparent when a measurement is made. According to the principles of quantum mechanics, a property of a particle, such as its spin or its polarization, is not determined until it is measured. It exists in a probabilistic superposition of all possible states. But for an entangled pair, the moment you measure a property of one particle, you instantly and definitively know the corresponding property of its distant partner. For example, if two electrons are created with a total spin of 0, and you measure the spin of 1 to be up along a certain axis, you know with absolute certainty that its entangled partner, even if it is on the other side of the galaxy, will be found to have a spin of down along the same axis. It is as if the two particles are engaged in a perfect, instantaneous, and silent conversation, a form of communication that seems to be faster than the speed of light, a clear violation of one of the most sacred principles of Einstein's theory of relativity. Albert Einstein himself was deeply troubled by this aspect of quantum mechanics. He famously and derisively referred to it as spookhafte Fernwirkung, or spooky action at a distance. He believed that this apparent faster-than-light connection was a sign that the quantum theory was incomplete, that there must be some hidden variables, some local, predetermined instructions that the particles carried with them, which would explain the perfect correlation of the measurement outcomes without the need for any spooky, non-local influence. For decades, this was a philosophical debate. But in the 1960s, the physicist John Bell devised a brilliant mathematical theorem, now known as Bell's theorem, which showed that it was possible to design an experiment that could definitively distinguish between the predictions of quantum mechanics and any theory based on local hidden variables. In the decades since, numerous Bell test experiments have been performed with ever-increasing precision and sophistication, and every single one of them has confirmed the predictions of quantum mechanics and ruled out local realism. The spooky action is real. The universe, at its most fundamental level, is non-local. The reality of quantum entanglement has profound and far-reaching implications, not just for physics, but for our entire understanding of the nature of reality. It is crucial to understand, however, that entanglement cannot be used to transmit information faster than light in a controllable way. The outcome of a measurement on one of the entangled particles is fundamentally random. You cannot choose whether you will measure spin up or spin down. You only know that your friend at the other end of the galaxy, upon measuring their particle, will get the opposite result. It is only when you later compare your results, a process that is still limited by the classical speed of light, that you can see the perfect, spooky correlation. Entanglement allows for correlation, but not for communication. And yet, the underlying instantaneous connection is undeniably real. It tells us that our classical picture of a universe made up of separate, independent, and localized objects is a profound illusion. At a deep and fundamental level, the universe is not a collection of things. It is an indivisible, holistic, and interconnected whole. The concept of separateness is an emergent property of our macroscopic world, an approximation that works well for everyday objects, but breaks down completely in the quantum realm. This has deep philosophical and even spiritual resonances. It suggests that the sense of separation we experience as individual beings, the feeling of being a skin-encapsulated ego, as the philosopher Alan Watts called it, is not the ultimate truth of our existence. We are all, in a very real physical sense, entangled with each other, with the planet we live on, and with the cosmos as a whole. The atoms in our bodies were forged in the hearts of stars, their quantum states entangled with the other atoms that were created alongside them. We are literally made of stardust, and we carry within us the entangled history of the universe. Could the more subtle and mysterious aspects of human experience, the profound sense of empathy that can exist between two people, the strange synchronicity of thinking of a loved one just moments before they call, The powerful feeling of collective consciousness that can emerge in a crowd or a ritual be a macroscopic echo of this fundamental quantum entanglement. These are speculative questions, to be sure, and they are far from being scientifically proven, but they are questions that are becoming increasingly legitimate to ask. As our understanding of the quantum nature of biological systems grows, we may find that the brain itself is a kind of quantum information processing system, one that is capable of engaging with the non-local, entangled nature of reality in ways that we are only just beginning to imagine. The practical applications of quantum entanglement are no longer the stuff of science fiction. They are at the heart of the emerging technologies of the 21st century. The field of quantum information science is built upon the idea of harnessing the strange and powerful properties of the quantum world, like superposition and entanglement, to process and transmit information in new and revolutionary ways. We have already touched upon quantum computing, where entangled qubits can be used to perform calculations that are far beyond the reach of any classical computer. But entanglement is also the key to a new and unbreakably secure form of communication, quantum cryptography. The most well-developed of these schemes is called quantum key distribution. In a QKD system, two parties, let's call them Alice and Bob, can generate a shared secret key by exchanging a series of entangled photons. They can then use this key to encrypt and decrypt their messages. The security of this system is guaranteed by the fundamental laws of quantum mechanics. If an eavesdropper, Eve, tries to intercept and measure the entangled photons to learn the key, her very act of measurement will inevitably disturb the delicate entangled state. This disturbance will be instantly detectable by Alice and Bob when they later compare a subset of their measurement results. They will know that their communication channel has been compromised and can discard the key and start over. Unlike classical cryptography, which relies on the computational difficulty of solving certain mathematical problems, the security of quantum cryptography is based on the fundamental principles of nature itself. It is, in a sense, a perfectly secure form of communication. Entanglement is also being explored for its potential in creating new forms of quantum sensing. By creating entangled states of multiple particles, it is possible to build sensors that are far more sensitive than any classical device. For example, entangled photons can be used to create quantum imaging systems that can see objects with a resolution that surpasses the classical diffraction limit of light. Entangled atoms can be used to build quantum clocks that are so precise they would not lose or gain a second in the entire age of the universe. These ultra-precise clocks have applications in everything from fundamental physics tests to next-generation GPS systems. The journey to build these quantum technologies is a long and challenging one. Entanglement is an incredibly fragile and delicate state, easily destroyed by any interaction with the environment. But the progress in the last few decades has been astonishing, and we are now on the verge of a true second quantum revolution, a revolution that will be driven by our growing ability to control and manipulate the strange and beautiful reality of quantum entanglement. It is a revolution that will not just give us faster computers and more secure communication. It will fundamentally change our relationship with the world, allowing us to interact with nature at its deepest, most interconnected, and most mysterious level. The uncertainty principle, with its inherent limit on our knowledge, is not a statement of scientific failure, but a profound and beautiful revelation about the dynamic and creative nature of the universe. It tells us that reality, at its core, is not a static, predetermined machine that can be perfectly known and predicted, but a fluid, vibrant, and endlessly unfolding process. The trade-off between position and momentum, between energy and time, is not a flaw in our theories. It is the very source of all stability and all change in the cosmos. It is the quantum law that prevents the universe from collapsing into a state of perfect, static, and lifeless certainty. This fundamental principle, which governs the behavior of the smallest particles, is also a powerful and insightful metaphor for the nature of our own minds and for the art of living a meaningful and creative life. We often crave certainty. We want to know the future, to control our circumstances, to have a fixed and stable sense of who we are. We want to pin down both our precise position in life, our identity, our status, our place in the world, and our momentum, our direction, our purpose, our path forward. But the uncertainty principle suggests that this is an impossible and perhaps even undesirable quest. The more we try to fix our identity, to cling to a rigid, unchanging sense of self, the more we lose our capacity for growth, for movement, for change. Our momentum becomes uncertain. We become stuck, brittle, and defensive. Conversely, the more we become obsessed with a single, linear path forward, a single goal, a single definition of success, the more we can lose touch with the richness, the complexity, and the beauty of our position in the present moment. We become ungrounded, disconnected from the very source of our own aliveness. A healthy, creative, and fulfilling life, like a stable quantum system, is a dynamic and graceful dance between these two complementary poles. It is a process of finding a balance between the security of being and the adventure of becoming, between the rootedness of our present reality and the open-ended possibility of our future. Sleep is our nightly and natural immersion into this dance of uncertainty. As we drift off, the conscious, controlling, and certainty-seeking mind of the ego relinquishes its tight grip. We let go of our need to know, to define, to predict. We surrender ourselves to the gentle, welcoming embrace of the unknown. And in this surrender, the mind is set free. The rigid, linear tracks of logical thought give way to the fluid, associative, and dreamlike currents of the unconscious. This is the hypnagogic state, the creative, fertile ground between waking and sleeping, a state that has been the source of inspiration for countless artists, scientists, and innovators throughout history. It is a state where the uncertainty is not a problem to be solved, but a creative space to be explored. In the dream state proper, this exploration becomes a full-blown symphony of the imagination. The normal rules of logic, of causality, of time and space are beautifully and playfully suspended. We can be in multiple places at once. We can be different people. We can experience a reality that is built not on the linear logic of cause and effect, but on the deep, associative logic of emotion and symbol. This is not a state of chaos. It is a different, and perhaps more fundamental, kind of order. The uncertainty principle is not a pessimistic statement about the limits of our knowledge. It is a cosmic permission slip, an invitation to embrace mystery, to dance with the unknown, to find peace not in the illusion of control, but in the wise and graceful surrender to the beautiful, unpredictable, and endlessly creative music of an uncertain universe. And every night, as we close our eyes and let go of the day, we are attuning ourselves to this fundamental cosmic rhythm, a rhythm that is the very source of all life, all creativity, and all change. The concept of superposition, the idea that a quantum particle can exist in a multiplicity of states at the same time, is a direct challenge to the either-or logic that governs our classical macroscopic world. It introduces a both-and reality, a reality where contradiction is not a sign of error, but a fundamental feature of existence. This is a concept that is not just confined to the esoteric world of physics. It is a deep and resonant truth about the nature of our own human experience. We are not single, monolithic beings. We are a complex, dynamic, and often contradictory superposition of different selves, different desires, different beliefs, and different potential life paths. We contain, as the poet Walt Whitman wrote, multitudes, The confident self and the insecure self, the compassionate self and the angry self, the adventurous self and the cautious self, all of these and many more coexist within the vast quantum field of our own psyche. We often experience this inner multiplicity as a source of conflict, of indecision, of anxiety. We want both the security of a stable job and the freedom of a creative life. We feel both deep love and profound irritation towards the people closest to us. We hold political or religious beliefs that are, upon closer inspection, full of internal contradictions. We tend to see this as a problem to be solved, a sign of our own inconsistency or lack of integrity. But from a quantum perspective, this inner multiplicity is not a flaw. It is the very source of our richness, our complexity, and our capacity for growth. It is the superpositional nature of our own being. In our waking lives, we often try to resolve this inner tension by identifying with one aspect of ourselves and suppressing or disowning the others. We collapse our rich, complex wave function into a single, coherent, and socially acceptable persona. But the other, unchosen possibilities do not simply disappear. They continue to exist as a latent potential in our unconscious, and they often make their presence known in the strange, symbolic, and multiplicitous world of our dreams. Sleep is the great theater of our inner superposition. As the conscious ego, the director of our waking life, takes a rest, all the other actors in our inner drama are given a chance to come on stage. In our dreams, we can be both the hero and the villain, the victim and the perpetrator, the wise elder and the foolish child. We can experience a reality from multiple perspectives at once. We can live out the consequences of the choices we did not make in our waking lives. This is the psyche's way of exploring its own vast landscape of potential. It is a process of dialogue, of negotiation, of integration between the different and often conflicting parts of ourselves. A dream is not just a random collection of images. It is a holistic, superpositional experience, a complex, multi-layered tapestry of meaning that speaks to the entirety of our being. This is why dreams can be so powerful, so transformative, and so healing. They allow us to access and to integrate the parts of ourselves that we have cut ourselves off from. They remind us that we are more than just the limited, partial identity we present to the world. They invite us to embrace our own inner contradictions, to hold the creative tension of our own multiplicity, and to become a more whole, more integrated, and more compassionate human being. The quantum principle of superposition is not just a strange feature of the subatomic world. It is a deep, psychological, and spiritual truth. It is a truth that we are invited to experience, to explore, and to embrace in the most profound and personal way. In the silent, mysterious, and beautifully superpositional reality of our own sleep. At the heart of quantum mechanics lies the enigmatic figure of the observer, a figure that seems to blur the line between the subjective and the objective, between the mind and the world. The observer effect, the fact that the very act of measuring a quantum system changes its state, is one of the most profound and unsettling discoveries in the history of science. It tells us that we are not detached, passive spectators of a pre-existing reality. We are active participants in a participatory cosmos, a universe that seems to respond to, and to be shaped by, the very act of our observation. The double-slit experiment is the classic demonstration of this. When we are not looking, an electron behaves like a wave, passing through both slits at once. When we look, it behaves like a particle, choosing a single path. Our observation, our inquiry, seems to be a creative act, a force that collapses the ghostly, probabilistic world of quantum potential into the solid, definite world of classical actuality. This is a concept that has deep and powerful implications for our understanding of our own role in the shaping of our reality. The world we experience is not a raw, objective reality that is simply out there. It is a co-created reality, a reality that is born in the interaction between the vast, superpositional potential of the universe and the focused, collapsing power of our own consciousness. Our attention is not a passive spotlight that simply illuminates what is already there. It is a creative force that helps to bring what is there into being. The beliefs we hold, the questions we ask, the quality of our attention, all of these act as a kind of measurement that collapses the wave function of our own experience. If we approach the world with a mindset of fear, of lack, of cynicism, we will tend to selectively perceive and amplify the evidence that confirms that worldview. The world will, in a sense, become the world we expect it to be. If, on the other hand, we can cultivate a gaze of curiosity, of compassion, of appreciation, we can begin to collapse a different kind of reality. A reality that is richer, more beautiful, and more full of possibility. This creative act of observation is not limited to our waking lives. Sleep is a time when the observer turns inward. The lens of our consciousness, which is usually directed at the external, sensory world, turns to face the vast inner landscape of our own psyche. And in our dreams, we are both the creator of the dream world and the observer within it. The landscapes, the characters, the narratives of our dreams are a direct and unfiltered manifestation of our own inner state. But they are not just a passive reflection. The way we interact with the dream, the way we observe it from within, can change its course. In a lucid dream, where we become aware that we are dreaming, this power becomes explicit. We can consciously choose to confront the frightening monster, and in doing so, we may find that it transforms into a helpful guide. We can choose to fly, and in doing so, we collapse the wave function of the dream world in a way that makes flight possible. Lucid dreaming is a powerful training ground for the participatory nature of reality. It teaches us that our awareness is a creative force, that our intention can shape our experience. But even in ordinary dreams, this process is at play. The dream is a constant feedback loop between the unconscious observer and the dream world it is creating. It is a dialogue, a dance. The observer effect is not just a strange quirk of physics, it is a sacred responsibility. It is a call to become more conscious of our own gaze, to recognize its power, and to learn to look at ourselves, at each other, and at the world with a quality of attention that is worthy of the beautiful, mysterious, and participatory cosmos we inhabit. The wave function, the central mathematical object of quantum mechanics, is more than just a tool for calculating probabilities. It is a poetic and powerful map of the hidden, potential nature of reality. It tells us that the universe, at its core, is not a world of solid, definite things, but a shimmering, vibrant sea of possibility. A particle is not a point. It is a wave of potential, spread out in space, containing the possibility of being found here, or there, or anywhere in between. The wave function is the mathematical description of this field of potential. It is the score for the cosmic symphony. A symphony where the notes are not fixed, but are a superposition of all possible tones, waiting to be played. This is a vision of reality that is deeply resonant with our own subjective experience of life. Our lives, too, are a wave function. Our future is not a single, predetermined path, but a superposition of all possible futures. Every moment is a crossroads, a point where the wave function of our life can collapse into a new, definite state, setting us on a new trajectory. The thoughts, the feelings, the desires that flicker through our minds are the ripples on the surface of this deep, potential sea. The what-ifs, the daydreams, the imagined scenarios. These are not just idle fantasies. They are the exploration of our own personal wave function, the tracing of the different, possible paths that our lives could take. And sleep is the time when we dive most deeply into this ocean of possibility. In the waking state, our consciousness is largely a collapsed wave function. We have made our choices. We are on our path. Our reality is, for the most part, definite and singular. But as we fall asleep, the collapse is undone. We decohere from the classical world and re-enter the quantum realm of pure potential. In our dreams, we are no longer bound by a single reality. We can experience a multitude of possibilities simultaneously. A dream is not a linear narrative, it is a holistic, superpositional experience, a cross-section of our own personal wave function. It can contain echoes of the past, premonitions of the future, and symbols of our deepest, timeless nature, all woven together in a single, multi-layered tapestry of meaning. To interpret a dream is to act as an observer, to collapse its rich, superpositional meaning into a single, conscious understanding. But the dream itself, in its raw, uninterpreted state, remains a pure expression of possibility. It is a reminder that our reality is not as fixed and solid as it appears. It is a reminder that we are always, at every moment, standing at the edge of an infinite sea of potential. The wave function is the universe's most beautiful and profound poem. It is a poem written in the language of mathematics, a poem that speaks of a reality that is not made of things, but of possibilities, not of certainties, but of dreams. And every night, as we close our eyes and surrender to the gentle, wave-like currents of our own consciousness, we are given the chance to read a few more lines of this endless cosmic verse, and to remember the deep, beautiful, and liberating truth of our own infinite potential. The universe, as described by modern physics, is a story of two grand and seemingly incompatible narratives. On the one hand, we have Einstein's theory of general relativity, the story of the large-scale cosmos, a world of smooth, curved spacetime, of galaxies and black holes, a world governed by the elegant, deterministic laws of gravity. On the other hand, we have quantum mechanics, the story of the small-scale world, a world of discrete particles, of probabilistic jumps, of uncertainty and superposition. These two theories are the twin pillars of modern physics, and each has been confirmed with unprecedented accuracy in its own domain. But they do not seem to speak the same language. They are based on fundamentally different principles and mathematical formalisms. Finding a single, unified theory that can encompass both a theory of quantum gravity is the single greatest challenge in all of theoretical physics. It is the Holy Grail, the quest to find the single, underlying law that governs the entire cosmos, from the subatomic to the cosmological. This tension between the large and the small, the continuous and the discrete, the deterministic and the probabilistic, is not just a problem for physicists. It is a tension that we all live with, a fundamental duality of our own experience. We live in the macroscopic, classical world of our bodies, a world governed by the seemingly predictable laws of gravity and motion. But our minds, our consciousness, often seem to operate on a different logic, a logic that is more akin to the quantum world, a world of fluid associations, of nonlinear time, of superpositional states. Sleep is the realm where this tension between the two worlds is most acutely felt, and perhaps where a bridge between them can be found. As we fall asleep, our consciousness detaches from the classical sensory world and enters a state that is deeply quantum-like. In our dreams, the normal laws of physics are suspended. We can fly, defying gravity. We can pass through walls, an act of macroscopic quantum tunneling. We can be in multiple places at once, a direct experience of superposition, The scale of our experience becomes fluid and dynamic. In one moment, we can feel as vast as a galaxy, our consciousness expanding to fill the cosmos. In the next, we can feel as small and insignificant as a single grain of dust. This constant shifting of scale, this effortless movement between the macro and the micro, is a hallmark of the dream state. It is as if our dreaming mind is a natural quantum gravity simulator, a place where the rigid distinctions between the large and the small dissolve, and a more unified, holistic reality is experienced. Could it be that the structure of our own consciousness is a clue to the structure of the universe? Could the way our minds bridge the gap between the concrete, physical world and the abstract, symbolic world of thought be a reflection of the way that nature bridges the gap between gravity and the quantum? This is a speculative but deeply compelling idea. It suggests that the answers to the deepest questions of physics may not just be found in particle accelerators or space telescopes, but also in the deep, introspective exploration of our own inner worlds. Sleep, in this view, is not just a biological function. It is a nightly journey to the very frontier of our understanding, a place where the two great warring narratives of the universe can meet, can dance, and can perhaps, in the symbolic, poetic language of our dreams, find a way to become one. The unresolved tension between gravity and the quantum is not just a problem for science. It is the central, creative tension of our own human existence, a tension that we are invited to explore, to hold, and to integrate in the deep, mysterious, and unifying space of our own sleep. In the final analysis, the deepest mystery that the quantum world presents us with is not about particles or waves, but about ourselves. The journey into the heart of the atom has led us unexpectedly to the threshold of our own consciousness. The discovery that the observer is not a detached spectator, but an active participant in the creation of reality, has forced science to confront a question it has long sought to avoid: what is the nature of the observer? What is this thing we call consciousness that seems to hold such a privileged and powerful place in the cosmic drama, the classical materialistic worldview, which has dominated science for centuries, sees consciousness as an epiphenomenon, a secondary and accidental byproduct of complex neural computation in the brain. It is a ghost in the machine, a strange and wonderful illusion, but ultimately not a fundamental aspect of reality. But the quantum world seems to hint at a different, more radical possibility. It suggests that consciousness may not be a late-coming accident in a dead, mechanical universe, but may be a fundamental, irreducible, and perhaps even primary aspect of the cosmos itself. This is the central tenet of a philosophical position known as panpsychism. The idea that consciousness, in some rudimentary form, is a property of all matter. In this view, an electron does not just have mass and charge, it also has a tiny, primitive flicker of subjective experience. As matter becomes more complex and organized, as in a living cell or a human brain, this rudimentary consciousness can combine and complexify, giving rise to the rich, self-aware consciousness that we experience. This is a staggering idea, one that completely inverts our normal understanding of the world. It suggests that the universe is not a collection of dead matter that somehow, miraculously, gives rise to consciousness. It suggests that the universe, from its very beginning, has been imbued with a potential for awareness, and that we, as conscious beings, are not a strange anomaly, but a natural and beautiful expression of this fundamental cosmic property. In this worldview, the quantum field is not just a field of energy and potential, it is also a field of nascent consciousness. The entire universe is a single, vast, and interconnected mind, and our individual consciousnesses are like eddies in this great cosmic stream. This is a vision that has been expressed in different forms by mystics and philosophers for millennia: the Brahman of the Vedanta, the mind of God of the Hermetic traditions, the anima mundi of the Platonists. These are all expressions of the same deep intuition that consciousness is the ultimate reality. What is new is that this ancient spiritual intuition is now finding a tentative but growing resonance with the cutting edge of modern physics. The puzzles of the quantum world, the observer effect, entanglement, the nature of time may all be clues that are pointing us towards a new, post-materialist paradigm. A paradigm that recognizes the fundamental role of consciousness in the structure of reality. And sleep, once again, becomes our most intimate and direct portal to this deeper reality. As the conscious individual ego dissolves, we are given the chance to merge back into the universal field of consciousness from which we arose. The dream state, with its symbolic language, its non-local connections, and its creative power, may be a direct experience of the mind of the universe, expressing itself through the unique filter of our own personal history. To fall asleep is to remember our cosmic origins. It is to let go of the illusion of our own separateness and to reunite with the single, unified, and conscious field that is the source of all being. We are not just in the universe. The universe is in us. We are the universe's way of knowing itself, of feeling itself, of dreaming itself into existence. And the greatest secret of the quantum world may be a secret that we have known all along, in the deepest, most silent, and most sacred chambers of our own conscious hearts. The strange, paradoxical, and beautiful world of quantum mechanics is not a distant, abstract realm of interest only to physicists. It is the very ground of our being, the invisible, energetic, and conscious foundation upon which our entire reality is built. The principles of superposition, of uncertainty, of entanglement, are not just descriptions of subatomic particles. They are deep, resonant metaphors for the nature of our own minds, our own lives, our own souls. The universe that the quantum revolution has revealed is not a cold, dead and deterministic machine, but a living, breathing, and participatory cosmos. A universe that is constantly being co-created in the dance between potential and actuality, between the observer and the observed. And sleep, the state we enter every night, is our most profound and direct access to this quantum reality. It is a nightly pilgrimage to the source, a journey into the superpositional sea of our own consciousness, a surrender to the creative uncertainty of the void, an immersion in the entangled web of our own interconnectedness. To understand the quantum world is to understand ourselves in a new and deeper way. It is to recognize that we are not fixed, solid, and separate entities, but fluid, multi-layered, and deeply connected beings. It is to embrace the paradox of our own nature, to honor both the particle of our individual existence and the wave of our universal connection. It is to find a new kind of freedom, a freedom that comes not from control, but from surrender, a freedom that is born from the recognition that at the heart of reality lies not a rigid certainty, but an infinite, creative, and beautiful mystery. The journey into the quantum realm is a journey home, a journey back to the fundamental, magical, and dreamlike nature of our own true being. And every night, as we close our eyes and drift into the gentle, quantum sea of sleep, we are given the chance to remember, to heal, and to be reborn.